So whoever said that you could not take an entire computer science class and explain all of it in 10 minutes? That's what I'm going to try to do here. We're going to talk about data structures, and I'm going to do it in a two-part episode. The first video is going to be the conceptual theory behind data structures, and then the second part is going to be code, where I actually show C++ code that uses data structures and explain how the standard C++ data structures work. So let's get started. The first concept that I want to mention with respect to data structures is asymptotic complexity. And essentially, the problem is when you're dealing with all these different data structures, you need to find a way to rate the performance of algorithms. And because data structures are fundamentally collections of algorithms, we can use this asymptotic complexity to rate the performance of the data structures, as opposed to just the data structure or the performance of the algorithms that encompass them and make them up. So it's a way for us to compare different data structures because we need to have some kind of a basis for comparison. So the most important thing that you probably would want to take away from this whole video is that there is no one correct data structure to use. There's no data structure that's going to be a silver bullet that's going to be the optimum one to use in all situations. However, it's also important to note that asymptotic complexity, which I'm about to explain in more detail, is one of those things that only really starts to make a significant difference when you start dealing with very, very large scales of data, very, very large amounts of data that you're going to be working with, which can happen in games very often, but when you're making something like Mario, it might not happen. Nonetheless, it's still good to know this stuff. So asymptotic complexity brings with it the most probably recognizable concept in computer science, even from people that don't do it on a regular basis, and that's the concept of big O. And I'm going to tell you all about what big O is. So big O is mathematically defined as the upper bound on the complexity of an algorithm. Some people also refer to it as the worst case. In other words, how will this algorithm scale, and how will it perform as the data size grows, which we represent using a lowercase n. So as n, which is just sum proportional to the size of the data, as the size of the data grows, how will this algorithm scale? How good is the algorithm with respect to basically how well does that do when n starts to grow very large? I should have probably put there that the reason why it's called asymptotic is because you're thinking about what happens when n gets very large, not just a little bit large. And computers nowadays are gigahertz in speed, so you can do quite a bit before these changes start to come into light. So this is denoted as big O of n, and that's why they call it big O, uppercase O or big O of n. And that's the asymptotic function of n. How does it perform? There is an entire field of study dedicated to this area, and we are going to drastically simplify it. If you think that you're going to walk away from this YouTube video being an expert in big O, you're freaking wrong. But I'm at least going to explain it to you because you can't talk about data structures without talking about big O. So, big O helps us classify algorithm complexity, and I'm going to go over the most popular classifications of algorithms. So constant time, or big O of 1, is the fastest or simplest complexity class of an algorithm. And basically what that means is as n, or as the number of the size of data grows, the complexity of the algorithm is constant, meaning it will never grow at all as n gets large. It will be constant time. It could be a very large constant. You could have a function that takes 50 years to finish, but as the number of items in your data structure grow, it remains 50 years. It never gets any worse. That's a terrible example, but you get the idea. It's constant. Logarithmic is a complexity type that's usually referred to as O of log n, or the logarithm of n. And what this basically says is it grows, the complexity of the algorithm grows with n, but in a sublinear fashion. In other words, it's guaranteed to level off after a while, such that if I was to grab my mouse here and follow this curve, eventually there's going to be some asymptote here that this curve will never pass, and that's usually the logarithm base. So for example, if you had a logarithm base 2 algorithm, which is very common in data structures, this thing would never go greater than 2. So logarithmic algorithm complexity isn't as good as constant, but it's considered very good. Linear, on the other hand, is where you start to run into algorithms that are considered rather complex and algorithms that don't scale as well as you would like. As n increases, as the size of your data that you're computing over increases, so does the algorithm amount of time it takes, or the complexity of the algorithm grows linearly with the data size. Example of a linear algorithm would be a simple iterative find, where you loop through an array and you want to see if you're looking for a specific item in the array and you just naively iterate over it. That would be what's called an O of n, or a linear algorithm. Polynomial is when things start to really suck. Polynomial time algorithms are O of n squared or n cubed, so forth. I always just consider them all together in the class of O of n squared. Polynomial time is considered rather poor. You can see that as n grows, the function itself grows almost in a parabola. It tends to, if you had linear here, you notice it grows much faster than linear. It almost kind of approaches this asymptote, since it's the inverse of a logarithm, almost like way towards the sky. An example of a polynomial time algorithm would be searching for any element of one array in any other element of another array. So you have to iterate over both of them. So as the n increases, you have to look over a square of that many items. Polynomial time is considered rather poor. Even worse than that is exponential time, which is considered big O of c to the n, where c is some constant. That's a disaster. If you ever encounter an exponential time algorithm, then you're a computer science major and you hate your life. This is not very common to run into these. There are a few others that I haven't mentioned. O of n factorial. Just if you ever write an algorithm that's n of factorial, you should take your laptop and throw it out of the balcony, or run over it with your car, dip it in the toilet. It's just game over. Forget it. O of n log n fits somewhere in between linear and exponential. It's less efficient. It scales more so than a linear, but less than an exponent. It's kind of somewhere in between the two. I've always kind of considered n log n as logarithmic, which may not be correct to some of the computer scientists listening, but it's one of those things where it's good to recognize that there's a difference between log n and n times log n, So, and some others that I probably forgot about, but the most important ones I've covered. So you're probably wondering at this point, what the hell does any of this have to do with C++? Well, I'm glad you asked, inquisitive guy, you. Data structures are built into C++. What I mean by that is C came with no facilities for working with data structures, with the exception of the built-in array, which is a data structure in of itself, a very simple one. On the other hand, C++ has plenty of built-in data structures that come with the library, and what's called the standard template library, or the STL for short. So what are some of those? Well, there's maps. There's hash tables, which are not directly exposed, but certain maps in C++ are implemented using those. There are sets. There are trees, which again are not directly exposed to C++, but are many sets, and some maps are implemented using trees. There are vectors, which you can think of as almost exactly the same as arrays, but they are dynamic. In other words, when you want to add elements to them beyond their original size, they will automatically grow. And there are linked lists, which are linked lists. There are also not graphs. Graphs are not provided in C++. However, I'm pretty sure someone watching this video that might already know quite a bit about data structures, if I didn't mention the word graphs at all, would put a comment down there in the comments and be like, you can't talk about data structures without mentioning graphs. So here's me mentioning graphs. Fuck graphs. That's all I'm going to say about graphs. So what are some of the what are some of the properties of these data structures that come with C++? So the first one is standard vector. Standard vector, like I said, is an abstraction of an array in C++, but it can do things that arrays can't do because it's a higher level. You can think of it almost as an encapsulation of an array. So what can you do with a vector? Well, you can insert an element, you can find an element, you can access the nth element, and one major important property of vector, which is not very common, I think, in any of the other STL data structures, is that the memory, or the elements of that array are contiguous in memory. So what do I mean here with O of n and stuff? So basically, I looked up the rated performance of all these algorithms, or better yet, the rated complexity in terms of big O. So what this says basically is that if you want to use a vector, you will find that if you want to insert an element in the middle of the vector, that complexity of that operation for vector is O of n, it's linear. If you want to find an element in a vector by its value, just search for some number or whatever, something by its value, that's O of n, that's linear. It's in red because that's considered reasonably poor scalability. However, if you want to access the nth element, like you could in array access array sub bracket I, or n in this case, that is considered and guaranteed to be O of 1, or constant time. That's what random access means. I don't want to get all philosophical on you guys right now and go off on a tangent, but RAM is random access memory. That's what RAM stands for. RAM is one giant ass array. It's one giant vector. So that's the reason why RAM exists, is that typically it's randomly accessed, and of course you're going to get O of constant time performance to do that. Inserting things in the middle of an array or finding an element within an array, that's not so good. So that's your vector. It's the most space efficient. So big O, one of the things that people get kind of upset is big O, most people talk about asymptotic complexity in terms of only time, the amount of CPU time it takes for something to run. When I think of data structures, it's very important to think about space as well, how much space and RAM this thing will take up. The vector is the most space efficient per size of any of the other data structures. That's important to note. What's the next data structure in C++? This one's standard list. Inserting an element in a list is O of 1, which is awesome. That's constant time. Finding an element, I believe, is O of n, except, yeah, that's about right, because you got to traverse the list. Accessing the nth element is also O of n. Linked lists only have information about the previous and next item in the list. So if you have the beginning of a list and you want to access the 100th item, you have to traverse over all 100 of them to get there. It's not random access. So it's not contiguous, but it's linked. Standard list is a doubly linked list, meaning you can go forward and backwards in the list. But you can't jump to the 20th element without incurring a penalty. That accessing the nth element is considered not very scalable. It is reasonably space efficient. It's not as space efficient as a vector because you have to create a separate allocation for every single item in the list, and that incurs overhead in RAM. Moving right along to the map. Inserting an element of a map, I always thought this was just logarithmic, but I looked it up and apparently it's n log n. Finding an element by key, this is important. Maps are indexed by key, not by value. So you could basically, if you wanted to have a map of things, you might say index by string to integers, so or index by string to pointers to other objects. It's always something where you index by something that's more user-friendly than an integer, which arrays are indexed by. I'll explain that a little better when I get to the code section. But in other words, finding an element by key is log n. It's purely logarithmic. Accessing the nth element is considered a pretty bad idea to do with maps, even though standard maps in C++ are in order. Typically, you don't use them to do this kind of thing, so I rate it as a linear or even worse performance. They're non-contiguous, and they are not space efficient. Believe it or not, the STL map is usually implemented using what's called a red-black tree, and trees tend to be even worse than lists as far as their space efficiency. They might do some pre-allocations and waste some memory in advance. One important thing I want to mention in the world of data structures is there is always a trade-off between space and time. The more space a data structure will take up, the less time it'll take to operate with it, if it's programmed not by an idiot. And the more time it'll take to work with a data structure, usually the more space efficient it'll be. So there's always that trade-off. It's almost like a physics thing where you can't create or destroy energy. The unordered map is something added to C++11. It's amazing because it finally is a hash map exposed directly to C++. I'm not going to talk directly about what hash maps are, just to know that they are a very efficient way of doing maps or indexes on items. And they are considered very performant. In other words, when you insert an element into a map, you tend to get constant time performance. I put on average there, and that actually breaks the whole concept of big O, because I believe it's called big theta instead, because big O is supposed to be a worst case. But it is on average constant time so much of the time that I've always considered maps or hash maps to be constant time, big O of 1, almost all the time. So again, when you want to find an element by a key, it's constant time on average, which is really good scalability. Access in the nth element, just like before, was kind of poor. You don't want to do that. The memory is mostly non-contiguous, and they are among the least space efficient of all the data structures, and that has to do with the fact that hash maps create these giant tables of memory, and most of it is wasted and not used, but it's done in a way so that you can almost it's hard for me to explain how hash maps work, but it's almost as if you're using the index directly as an index directly into an underlying array, which is too big to care about. The important thing to remember is that if you're using an unordered map, you're going to get very good scalability and performance inserting elements and finding elements by their keys. When you use the indexing aspect of them, they're great. And when I say insert, I also mean delete. It's kind of one and the same. If you want to erase something, you'll get the same scalability. Standard set, believe it or not, has the exact same characteristics asymptotically as the standard map, not the unordered map, the one that's implemented using a tree. And the reason why is because both sets and maps are implemented using the same red-black tree data structure underneath. And for that reason, you're going to get the same logarithmic and linear logarithmic complexity when you insert and find an element. The major difference between set and map being that you index by value instead of by key. So, you know, whether you're looking for something by its value versus some key which you use to index into it. I got a bad feeling I'm confusing the shit out of all you guys. But that's okay. Like I said, an entire computer science course in 15 minutes of slides. You know, what can you do? You can watch this more than once if you want. Eventually this makes sense, I promise, if you deal with it enough. One important thing I want to say about sets is that they are unique and they are always sorted. The unique thing is common to all sets and data structures. Sorted is something C++ just decided to do. But the cool thing about unique is that if you want to have a data structure where you're guaranteed that every item will only be in there once, so if you have a set of integers and you start adding 1, 5, 5, 7, 8, and then 10 a few times, each one will only be in there once. That can be very useful, especially when you're doing complicated algorithms with respect to things that you don't want being duplicated. It's non-contiguous. That's not news to anyone. And it's not space efficient. That's also not news to anyone. There's a few others that I haven't mentioned. There are stacks, queues, and singly linked lists. All three of these things are implemented using lists. They're just more restrictive versions of them. Stacks can only be pushed and then popped from the top. Queues can only be pushed to the back and then pop from the front, I think. Some idea of what's called a FIFO, first in, first out, and a LAFO, last in, first out. There are logical reasons and algorithmic reasons to use stacks and queues, but for the purposes of asymptotic complexity, they're identical, so I'm leaving them out. So when to use what data structure versus what? This is important because this is one area where computer scientists and game programmers, game programmers, everyone disagrees on this. This is like one of the biggest things. First off, you should always understand all this, for sure. If you don't understand it, if every carpenter's tool, if the only tool a carpenter has is a hammer, all his problems are going to look like nails, right? So if you don't know what a set does, you're just going to not use it when you should. So you should understand these data structures. That doesn't mean you have to use them at all the time. Jonathan Blow, which is a famous game developer and game designer, he takes this almost wild approach where he says you should never use any data structure but an array ever. And he says, you know, optimization is one of those things when you're working on a game that you should never do preemptively. You should only do when there's a problem. And I agree with him to a large extent, but I think he's kind of gone a little too far with respect to use arrays for everything at all times, because you can start running some pretty bad systems, especially if you know in advance the characteristics of the kind of stuff you're going to do. So this is the rule I follow. Generally, you know, for game programming, you know, if you're working on a NASA system and your damn rocket blows up and kills the Martian, don't blame me. You know, this should have like a disclaimer up here. You should be using maps when you're searching by a key. And what I mean is if you're ever using indexes where the index is a completely different type than the value that you're storing in there. Some people call these dictionaries, some people call them tables, some people call them maps. I tend to call them maps. If you're doing indexes, use a map. You should use a set when you're searching for something very often by value, because they're very good at finding something by value. Also, you should use a set when you care about uniqueness. You should use a list when you're doing many dynamic insertions and deletions in the middle of a data structure. You just should. That's a perfect case for lists to shine because they do insertions and deletions very quickly. And you should use vectors for just about everything else. Like I said, if the n value, or if the number of items that you're working with are very small, you can get away with using vectors for just about everything all the time. But there are some cases when your game that you're working on might scale. Maybe you start working on something along the lines that starting to look like World of Warcraft. Or maybe you're working on a game where you decide to have a game object for every single spark that comes from every single bullet shot by hundreds of enemies. You'd be surprised how quickly the computer starts to have a problem if you're using the wrong data structure. And that's why you should at least understand this stuff. Enough theory, you asshole. That's probably what someone's saying to me right now. And you're right. So that's the end of this YouTube video about the theory. We're going to jump into code next, and I'm going to provide you guys with an example of how to use one or two of these. I'm not going to go into 5 hours of a YouTube videos going over every possible one of those data structures. You guys are grown-ups, you can look them up. But I will at least cover a few of them and the ones that are commonly used to do a really nice game programming example. So that's coming up next.